All right, so today we're going to be working on pages 60 and 61. You see page 60 over here has the worksheet folded and glued down. And then page 61, we should have set up some KC notes with our learning target. Our title, energy bar chart notes, is what we're going to be writing about over here. It will not probably take up even the whole page, and our key terms and connections down below. You're probably going to want two different color pencils, not marker because marker bleeds through, but we'll be using these on the worksheet. It really doesn't matter which colors you pick. All right, so we're going to get a little bit of background information first, and then we'll be applying the notes that we're taking to the worksheet over here, and we'll do it kind of in chunks. So starting with the three types of energy accounts, there are about three. So in chemistry at least, there are three energy storage accounts. And the first one we're going to talk about is thermal energy. And if you remember from the previous day, we talked about thermal energy already, and we shorthand this as ETH. Okay. Thermal energy is whenever we're seeing a change in temperature. So when we were drawing our heating curve yesterday, it was in the center when the temperature was increasing from 0 to 100. We called this thermal energy. And in the worksheet that we're doing today, specifically, there's 4 different types of very scientific thermal energies that we talk about, or different temperatures that we talk about. So there's cold, there's room temperature, there's warm, and finally there's hot. Okay, we're going to be drawing bar charts, and each one of these 4 temperatures needs to be represented in terms of energy on the bar chart. The more bars you have, usually the more of that thing that you have. So when we're talking about energy, we're saying, well, if we're talking about something that's very hot, does that have a lot of energy or very little energy? And so hot versus cold, think about the way the particles are moving. They should be moving much, much faster when they're hot, therefore they have much more energy. So when we draw these on the bar charts, we're going to represent it with 4 bars of energy. Versus cold, particles are moving very slow, will be represented with only 1 bar. And then room temperature and warm will be in between. Okay? All right. So I am going to use red when I'm representing thermal energy on my bar chart. So just so you know, color coding sometimes helps. So we're going to switch over to the worksheet now. And I'll work through most, if not all, of this as we go. If you need to pause or rewind the video, please do that, because I'm really not going to pause and wait for you to catch up. I'm not sure where everyone's going to be at. So go ahead and pause when necessary. All right, so starting with only thermal energy, we have a problem here. A cup of hot coffee cools as it sits on the table. This is what I call energy bar charts, or sometimes you'll hear me call them LOL charts. LOL, get it? Okay. Anyway, so we're going to draw a bar chart before and an after, and then this center part represents the system, and we're going to show the change from the before to the after here in the center. So we're talking about coffee. Go ahead and write coffee in that circle in the middle. And as you read it, it says it starts out as hot coffee, right? So in the beginning, it's pretty hot. And then it's going to cool to probably room temperature as it's sitting on the table. Okay? So hot, go back to your notes over here. Hot was 4 bars, right? So under where it says ETH, thermal energy, we're going to draw 4 bars. And then it goes to room temperature, and room temperature we said is going to be 2. So 2 bars. I have to switch pens. Okay, and this is thermal energy again. I said I was going to do red for this, so whatever color you chose, color that. Okay, we had 4, it went down to 2, which means we're losing energy. In fact, we're losing 2 bars specifically of energy. So that energy started out in the coffee. So I'm going to draw those 2 red bars that then get lost to the environment. And you can probably even see it as you see a cup of coffee sitting on the table. It maybe steams. You can see the heat kind of leaving that way. And there you go. 2 bars are lost to the system. And that's just thermal. So now let's continue on. There's another bank or account here of energy called EPH. So I'm going to jump back to notes. And we're going to talk about EPH. Okay, so the next account is called phase energy. In other words, EPH, which we also talked about the other day. And this isn't a change in temperature, so this is like that point in the heating curve graph when we were watching the water, and it flatlined, or it was consistent in temperature, but something else was happening during that time, and it was a change in phase, or a change in the state of matter. So we're going from like a solid to a liquid, or a liquid to a solid, vice versa, or even gas to liquid and liquid to gas. Those are all changes in state of matter. So the 3 states of matter also need to be assigned an amount of energy. Let's start with solid and liquid, and finally gas. Which one of those 3 has the most energy? So which one of those 3 are the particles moving the fastest? And that would be our gas. So we'll assign that 4 bars of energy when we're doing our bar charts. And then that means solid would be 1. And so you would assume liquid would be right in the middle, but honestly liquid has a lot less energy than gas, about half the amount. So let's just go 2. Okay, so use 1, 2, and 4 for phase energy. And so going back to problem number 1 with our hot cup of coffee. Okay, our hot cup of coffee, well, coffee is a liquid, right? So we would have 2 bars of energy. And even though it's cooling, as long as you didn't make some crazy jello kind of coffee, just because it's cooling, it doesn't change states of matter in this case. It stays a liquid, so we're still going to have 2 bars of phase energy. And so I'm going to color phase energy green. Okay. And so nothing changes there. And so I don't need to even draw any kind of green bars anywhere in my system. This middle part is only to show the change that happens from our before to our after. Okay, continuing on using both of those energies. Real fast though, let's make a quick note of the last one, which is ECH. So if you can make a guess, what do you think CH stands for? And there are many other kinds of energies as well, I should say that. If you take physics, there's force energies and gravitational energy, but in this case, we are only going to be talking about these three. And so the last type of energy is chemical. Okay, chemical energy is our ECH. And this is when you have a change in the type of substance. All right. We aren't going to really use ECH, especially not in this particular worksheet, but in the future we may. And the only time you use this is when we're creating new things. So only use if something new is made. Okay. All right. Just a little cheat, kind of add in here. We cooled a cup of coffee, okay? In general, when you cool something, you should see the same trend of energy being released. All right, the energy is leaving the system. So back here with our cup of coffee, you saw the energy started in the coffee and then it left, okay? So here's our system. Here's our energy bar. When it's cooling, it should leave, okay? Whereas if you're heating something, like the next one we're going to do, the opposite happens. Energy is actually being absorbed. Remember, cold cannot move. Only heat can. Heat is energy. So there's our system again. This time, our box of energy is going to go into the system. Okay? So that's generally what you're going to see, and you can always check back to this just to make sure you're doing things right. All right, so back to our worksheet here. We're going to do the next problem, whoops, where we have, and I can zoom in finally because we're kind of done with the notes, but we can refer back to them while we're doing this. A can of cold soda warms as is left on the counter. All right, so we have cold soda. So it starts out cold, and then it's warming up, so it probably can warm up to about room temperature. And soda, typically a liquid, just because it's warming up doesn't mean it's going to suddenly start evaporating. It doesn't talk about that at all. We're not heating it technically. It's just coming to room temperature, so it's still liquid. All right, thermal energy. If it's cold, how many bars? 1. If it goes to room temperature, though, that thermal energy is increasing to 2. And then our phase energies don't change. They stay at liquid, which would be 2 bars both times. All right. So I have 1 thermal, and then it goes up to 2. So when I draw my system in the center, the only change I should see is an increase or an addition of this 1 thermal box. So we're talking about soda here. Where is the energy coming from? It's being added to it. So again, we're heating something, even if it's just warming it by sitting out in the warmer air. It's heat going in. It's energy going in. Okay. Next one. Again, pause if you need to, but I'm going to keep on keeping on. So tray of water, 20 degrees Celsius is room temperature. 20 to 25 is room temperature. It is placed in the freezer, so it's going to get a lot colder. And this time it starts as water, or a liquid, and it turns into ice, which we all know, solid. So a couple things changing here. My thermal energy goes from 2 to much colder, 1. And then this time my phase is changing as well. It went from a liquid, which is 2, to a solid, which is only 1. Okay, so color that in. Looks like here in the thermal, we lost 1. So in our water here, 1 box at least, thermal box, is leaving. Okay, and then our phase goes from 2 down to just 1 as well. So we are lost another energy box, but this time it's 1 of each. There you go. So where does that energy go? You know, we're showing it leaving the water, but what's outside of the water? What is surrounding that in our freezer, which is air, right? So the energy from the water goes into the surrounding air. Which would be in the freezer. And then the freezer itself pulls that hot air out and pushes it into the kitchen air. You ever felt the side or the back, or even some of them that's at the top? It's kind of warm. And that's because the fridge is doing its job. It's pulling the energy out of your food or out of your water and forcing it then out into your kitchen. Okay, on to the inside, where things are just going to get harder and harder. Of course, that's how it seems to go, doesn't it? Hold on, I gotta adjust. Okay, number 5. So one of the ice cubes in number 3 is placed in a glass of room temperature soft drink, but we're going to make 2 different charts for this. So we're actually going to start with the ice, and then we're also going to look at the drink separately. So with the ice, it's starting pretty cold, I would assume. And then because we're putting it into some room temperature drink, I'm assuming that also is going to warm it up. And it's going to go from a solid, and then it'll probably melt into a liquid. Okay, so cold is 1 bar for thermal. Room temperature is 2. Solid is 1 bar for phase. Liquid is 2. So in this case here again, I'm gaining 2. If it's gaining energy, that means it's absorbing it, and it's absorbing 2 different kinds here. So color that all in. Gaining 1 thermal and gaining 1 phase. Well, we don't have to worry about chemical because when you freeze something or melt something, phase changes are always physical. Okay. The drink. So the drink started at room temperature. It's a liquid. And then because of the ice, hopefully the idea is you put the ice in there to make it colder. But it's still a liquid. And so we have 2 bars for thermal, decreasing to just 1. And then we have 2 bars for phase. That stays 2 because it didn't change states. And so here I lost 1. Must mean that 1 left. Goes from the drink out to the ice actually. So that's where that bar came from over here. All right. So describe how the arrangement and the motion of the particles in each system change from one to the next. Sorry, my pages keep falling over. Okay, so the ice. What are particles like in a solid? There, this is easier. They are organized and slow. But then, because we're warming up the ice and it's melting, they become more random as a liquid and faster. As for the drink, well, the drink doesn't change states of matter, so the arrangement of the particles isn't going to change. However, the particles are cooling down, so the particles will slow down. So this is a heating curve, or rather a cooling curve, which is kind of the opposite of what we talked about the other day, where when we were heating it up, the temperature was increasing, so it was going this way. Up the graph, it was still making like this S curve, but now we're cooling it, so we still have this backwards now S pattern, but it's going down. Let's say this represents like a cup of water, like a small little cup of water that you put in the freezer. What would it look like if you had a big bucket of water that you put in the freezer? Should take a lot longer, right? Just like it goes faster if you heat something faster. So we're going to take that same curve and we're just going to slow it down. It's going to take longer, stretch it out. When you're starting with a liquid, like water, that has random particles with medium speed, and then we're turning it into a solid, and these are organized. Let's see if I can do this without. And slow. What's happening in between? What is this flat plateau here where the temperature is no longer changing. So the temperature was going down, 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 and then it stopped. It just stayed the same for a while, and then it went down again. So again, this is like the opposite of what we were talking about the other day. And the other day when it was flat like that, it was melting or it was boiling. So in this case, it would be freezing. So it's going from a liquid to a solid here. Which is freezing. Okay. Some of the water you spilled in your shirt evaporates. So this sentence seems way more vague. It is a little harder, but we're still going to do our energy bar charts. So we have water, and it doesn't say anything about temperature, so I'm assuming it's like room temperature. And since it's spilled, it's got to be a liquid. And then it's on my shirt. Doesn't say it's warming up or anything, so don't read too much into it. It's still room temperature. And it's going to, I'm trying to move this over so it stays. It's going to heat up, or it's not going to heat up, but it evaporates now. So evaporates means it's turning into a gas, right? Okay, so room temperature, liquid, 2 bars, gas, which is now 4 bars. So thermal energy stays the same, but phase is changing quite a bit. And it's gaining. Okay, so these 2 bars here must have came from the outside going into the water, which causes it to evaporate. And you've probably seen this before, you know, if you leave a cup of water out for a while, or yes, you spill a stain on your shirt and then it evaporates off and it's not even damp or wet anymore. It can happen at room temperature. Water can evaporate at room temperature, or it can vaporize from boiling. All right, next page. All right, water vapor in the room condenses on a cold surface. So again, it doesn't really talk about temperature, but it's water in the air is what it's talking about here. Vapor means it's water in the air, and there is water in the air. During the winter, there's not as much. That's why it feels really dry and your lips dry out and you got to put some chapstick on. But there is such thing as water that's a gas at room temperature. And then condenses. So this is a word probably heard a long time ago when you're talking about the water cycle, but condenses means it's turning back into a liquid, and it's still at room temperature. So thermal energy is not changing. However, we're going from 4 in our phase energy down to just 2. And so we must be losing these 2. They're leaving the vapor out to the environment. All right, we got another 2-parter. In this one, we're not looking at 2 different systems. We're looking at the same system of water. However, it wants us to split it up into a point when it's just being heated and a point when it's actually being boiled away.